Okay, welcome to the section 9.1. What is energy notes review? Well, let's start by identifying what energy is. It's the ability to do work. Well, to really understand what that really means, you need to understand what work is. Well, work is any transfer of energy. And well, you think, well, if work is energy and energy is work, well, this is kind of a crazy concept. Well, work is done when a force moves an object through a distance. So when you're writing on your paper, you're technically doing work, but when you're sitting at your desk doing nothing, you are not doing work. So energy is transferred by a force moving an object through a distance. So in the case of writing with your pencil, the force is being exerted by your hand. Energy is being transferred from your hand to the pencil and making the pencil move. Both work and energy are measured in joules, and it's also pronounced joules. It can be either way. Alright, let's move on. You have kinetic energy. If you remember back to the matter unit, we had the kinetic theory of matter. And the kinetic theory of matter was the idea that the molecules were moving all the time. Well, it's called the kinetic theory of matter because kinetic energy is the energy of motion or movement. So they kind of go hand in hand. Depends on an object's mass and speed as far as how much it has. A missile moving as fast as a bullet will have more kinetic energy simply because it has a greater mass. Even though they're going the same velocity or speed. Because its mass is greater, it will do more damage. The same way as if you had like a smart car hits another car, or like a navigator. I mean, they're definitely going to do different kinds of damage because the mass is different, even if they're going the same speed. Potential energy is kinetic energy's brother, cousin, whatever you want to think about it as. They go together all the time. You can't have one without the other typically. They convert to and fro. And yeah, that's right, I just said to and fro. Energy that's stored as a result of position. Typically, the position of an object, obviously, but that's just like a generic potential energy definition. Let's move on to the more defined ones. Such as gravitational. Gravitational potential is this idea that an object's height really depends upon, that an object's potential energy depends upon its height above the ground. And it's called gravitational potential energy because, again, gravity is always constant. And if your mass changes, let's just imagine your mass doesn't change. But you had a mass of 5 pounds, and a 5-pound mass at a height of 1 foot off of the ground drops and hits your toe. It's going to hurt. There's no doubt about it because it's 5 pounds and your toe is pretty soft, and you're definitely going to feel it. However, if you drop that same 5-pound weight from about 5 feet, it's going to hurt a lot more. And the reason it hurts a lot more is because it has more energy. This is just a quick compare and contrast of potential and kinetic. You have this in your notes. Just kind of look it over. I think it's a good Venn diagram that kind of shows they're both forms of energy. They're both involved in mechanical motion or mechanical energy. But it does kind of show some of their differences in some of the examples. Okay, elastic potential energy has to do with any kind of object that's stretched or compressed. It doesn't have to be elastic in the material, but it has to be stretchable, really. That's what elastic means. Is, use it in clothes and stuff. But elastic, by definition, means that it's stretchable. Rubber bands are elastic. You have a good example of springs are very elastic. Bow and arrow has a lot of elasticity, and what gives it its energy. Okay, let's go ahead and move on from elastic. Back to mechanical. Mechanical, I really should probably move this slide back to where the kinetic and potential is, but it's what I was saying earlier about potential and kinetic being kind of brothers or cousins or whatever. You can't have one without the other. Mechanical energy is the energy of motion in general. You'll notice this energy of motion and position of an object. So what does that really mean? Energy of motion and position means it's kinetic and potential. So we really think of this as more of one concept called mechanical energy, but they can switch from PE to KE. As the man juggling the cats here shows, this cat has PE, this cat has KE because it's moving. But that will switch when he catches the next cat. Thermal energy is a review from matter. It just basically is the energy of particles or molecules. If you don't like the word particles, we can just use molecules of a substance or of matter. Solids being cold typically have a very close molecular structure. They don't vibrate that much, and because they don't vibrate that much is why they're cold. So the more a molecule vibrates, the hotter the temperature is. And again, this kind of comes back to kinetic energy, because the faster it moves, the more friction it's going to cause, and the more heat it's going to have. And of course, you can see this with the example of ice, right? Ice is really cold and it's solid. It's cold because it's solid. The molecules are not moving very fast. That's why it's cold. Steam, on the other hand, is hot when you remove the lid of your stove or off the pot off your stove. The steam is hot because it's a gas. It's escaped from the water form into the gas form, and now it's very excited and hot. The molecules are spread out. That's why it's hot, because they're kinetically moving around. So chemical energy. Chemical energy is actually formed when atoms are rearranged to form new compounds, which sounds weird, but it's actually it takes place every day, all the time, every day. It's one of the more common forms of energy transfer, actually. Food is a good example, right? We eat food because A, it's delicious, but B, it really gives us energy. Food is a chemical change in our body. When you eat it, your body breaks it down and restructures the food into different chemical compounds to give your body energy and the things it needs. Gasoline is another good idea of chemical energy. It's a liquid, you put it in your car, magically you turn the key and your car just works. It's not really that simple. But it's a chemical that converts when you apply heat to it to provide thrust, which is what makes your car go, really. Wood is another good example of chemical energy, because as you burn it, the chemical bonds rearrange, and you have, as a byproduct, you have heat and light. Electrical energy, again, we're going to talk more about this. We're going to talk more about this in another unit entirely, which is the electricity unit. But it's really the energy of moving electrons. And again, you see the word moving, you should relate that back to kinetic, and you'd be correct to do that, because electrons are kinetically moving all the time. Electrical energy, the beauty of it is it can be transformed into so many different types of energy. Sound energy, another form of potential kinetic, because as my example here poses, the guitar string is sitting there, or the piano string is just sitting there, and it has potential to have energy because it's pulled tight, but it's not going to have energy until it's either pulled or plucked, and then when it's released it moves, and that movement causes the sound energy vibrations. Light energy. again produced by vibrations of electrically charged particles. Well, if it's vibrating, it's what? It's moving. That's right. So the kinetic part, again, coming into play. Light has everything to do with the kinetic motion of electrons. So electricity and light, they're basically one and the same. I'm going to skip over some of this. This is a little more advanced than you really need, but I think it's kind of cool. So this is the EM spectrum, or it's better known as the EM spectrum. It's the electromagnetic spectrum. Here you see words you're probably familiar with: electro as in electricity, and magnetic as in magnetism. Electricity and magnetism go hand in hand. They're also related to electrons and the atom, and it's all related. Speed of light, 186,000 miles a second. It's just kind of a cool number to have. It's a good one to have in your brain. Nuclear energy, two different types. You have fission and fusion. Fission is the splitting of an atom, and like in a power plant, split atoms, large atoms, to make energy. We like to harness that energy for power, for nuclear power. Or you have nuclear fusion, and fusion is combining of two atoms to form a new one. So, for instance, the sun does this. Nuclear bombs do this as well. But both of them are considered nuclear energy because they're both associated with changes in the nucleus of an atom. This is where we get the word nuclear, because it has to do with the nucleus of an atom. This is fusion, kind of a diagram of fusion. Proton plus a proton comes in. It's typically hydrogen. It can be other ones, but it's typically hydrogen. A proton comes in, another proton comes in. Why is it hydrogen? Because they only have one proton. They come and smash together, and as denoted by this yellow star here, energy is created. Produces tremendous amount of energy. The sun is by far the largest energy producer in the entire solar system. And here again is fission. And of course Homer works at the nuclear power plant. This is what we do at nuclear power plants. We don't do fusion, we only do fission. And fission is the splitting of a large nucleus. Usually uranium or plutonium or something like that, which has like a large atomic mass, like about 256 or something like that. What it really means is it has like 250 protons and neutrons in here. So it's a rather large nucleus. Makes it an easier target to hit with a neutron. That's what we shoot it with. So we're able to throw a neutron in here and disrupt the entire thing because we're throwing it at such a high speed, and it splits it into two different new atoms, smaller atomic mass atoms, of course. Well, then you see neutrons flying off. Well, then as a byproduct, you have lots of energy created. And what kind of energy? Heat energy. So that's exactly what we use it for in a nuclear power plant. We harness the heat to boil the water, to force steam, to push the turbine, to create electricity. Anyway, that should be about it. I hope you enjoyed it and learned something. I will see you in class.